So at this point, hopefully you now have started to capture a good idea about the differences between our nucleophilic substitution, SN1, SN2, and our elimination reactions, our E1 and E2. One of the big challenges, though, comes from kind of trying to decouple what is going to happen. Are you going to go SN1, SN2, E1, and E2? And some of them there's a lot of similarities with their conditions. A lot of them have something that's going to be charged, a nucleophile or a base. A lot of them are going to have a leaving group. And trying to decide which one happens can sometimes be a little bit difficult. And we're going to kind of look at some strategies to try to differentiate between the competition of elimination and substitution. So first and foremost, there are going to be conditions that are going to favor one or the other. For example, we talked about that when we were talking about like our solvent conditions for like our SN1 versus SN2, whether or not it's a protic or aprotic solvent. And we're going to kind of build up a bunch of factors, and eventually we're going to get to a really nice table at the end where we have kind of some conditions that are going to favor one mechanism or the other. If you are checking all the tick marks for one mechanism in terms of conditions, that's going to be your dominating one. Where things get a little bit tricky is when you kind of get to the in-between, where you kind of have a Venn diagram and most of your conditions are kind of matching in the middle. You see that a lot with like secondary substrates. And at that point, you will then kind of need to determine which one's going to win out based on some different conditions. So the two that are going to overlap the most are going to be your ones together and then your twos together. So we talked about actually in the video when we're introducing E1 that SN1 and E1 happen on top of each other all the time. The other ones that can also happen or kind of be in competition a lot are going to be your twos, your SN2 and your E2. How do you know if you're going to go into the ones or the twos? And a lot of that's going to be based on your base or your nucleophile. If you have a good base or a good nucleophile, that's going to favor your twos over your ones. And when we say good base or good nucleophile, often that's going to mean something charged. So if you have a structure that has a physical charge on it, that's more likely to go into your twos than your ones. A lot of your weaker bases and your weaker nucleophiles are going to favor your ones. So one of my kind of first things I'm going to look at when I'm trying to differentiate is, do I have a strong or a weak base or nucleophile? And that's going to give me my one or two condition. We are going to talk a little bit about the difference between basicity and nucleophilicity and kind of comparing, and I'll give a handful of examples for common bases versus common nucleophiles. The next thing is going to be based on steric hindrance. The more sterics you have, the more likely elimination is going to happen. And that's going to be based on Zaitsev's rule. If you have a lot of stuff around, you're more likely to make a more substituted double bond. So let's go ahead and consider a series here. So here I have, in all of these, sodium methoxide. And I say sodium methoxide, sodium's just a counter ion, which we're not even going to draw in here. These are all going to be a strong base or nucleophile. So they are going to favor our twos over our ones. Here we have ethanol. That's going to be a protic solvent, meaning it can hydrogen bond because there's an OH. That's going to suppress SN2 a little bit. Now, here I have a alkyl bromide. So I have some carbon stuff and then a bromine. And you'll notice a big difference is the carbon that's connected to the bromine is either primary, secondary, or tertiary. Now, primary substrates are really going to favor our SN2. So if you actually run this reaction, you're going to get your diethyl ether and you're going to get your SN2 being your primary product. If you instead react this on a secondary, you can get some competition between your substitution and your elimination. So you will actually see both your SN2 product and you will also see your elimination product, which is going to be your E2 product. And you will see a mix of your SN2 and your E2. Now, if you are trying to predict your major product, you're going to think about your conditions. Now here, as I kind of mentioned, our solvent here is going to be protic. It can hydrogen bond because it has an OH. So that's actually going to suppress or slow down our SN2, and that's going to help make your E2 happen more. So in this case, your major product is actually going to be your E2, and then your minor product is going to be your SN2. If you change the solvent to maybe something like THF or DMSO, or choose any of the polar A products, that might switch, and then your major product might be your SN2. Now, when we think about our tertiary substrates, if we were doing a backside attack, that is really, really difficult on tertiaries, and that does not favor your SN2. SN2 is like methyl, primary, and secondary. So with this being a tertiary substrate, we can only do E2, and you're actually only going to get this product, which is your E2 elimination. So you can see here, just by changing your substrate, you can go from SN2 only to a mixture of SN2 and E2, and then based on your conditions, push it one direction or the other. And the last one, we only go E2 because of how sterically bulky it is. So there's just kind of like an example of something that looks remarkably similar, but can actually get completely different products. Now, when it comes to our next kind of set, or next kind of theme that we're going to be talking about, as you increase your nucleophilicity or your basicity, how strong that base is, that's going to push your reactions to whichever, your SN2 or your E2. Stronger nucleophile into the SN2, stronger base into the E2. Now, a stronger base is going to give more E2. A stronger nucleophile, which would be a weaker base, would favor your SN2. Now, let's go ahead and look at these two examples to kind of show that. So here we have and actually I'm going to make it like the exact same. I'll make that so the exact same structure. So we have the exact same structure, and then we're going to react this with sodium ethoxide or this deprotonated carboxylic acid. Now, if you go and you actually run this reaction, we kind of showed something pretty similar to above, that first reaction. That's going to be a secondary substrate, which gives us a mixture of SN2 and E2. So we can draw both an SN2 and an E2 product. The SN2 would be your substitution, and then your E2 would be an ugly looking double bond, something like that. I kind of changed that stereochemistry. You could also, if you wanted to show like the exact same stereochemistry, and if you wanted to show it like a Z configuration rather than a E, that's fine. So if you actually run this reaction and you actually look at the relative ratios, your SN2 is going to be your minor product, and it actually only has about a 20% yield, or 20% formed, where your major product is going to be your E2, which is going to be about 80%. Again, we noticed that because you had a protic solvent. You don't have to guess the percentages. Those percentages are experimentally determined. I'm just kind of giving you those so you can kind of see the relative difference. Now, we can do one of two ways to actually try to push this towards more SN2 conditions. The first one is we can change our solvent from a protic to an aprotic. So, for example, using DMF. The second thing we can do is change our structure. So the ethoxide is going to be a better base. If you add in your carbonyl there, what's going to happen is you can have some resonance. And that resonance, I kind of describe that as your structure kind of arguing with itself. So the lone pair can kind of come here and you can get some resonance. That's going to make this a weaker base or a stronger nucleophile. And that's going to actually then help favor the SN2. So in this case, your product's going to look pretty similar. The only thing that's going to change is you're now going to have the the carbonyl there on the substitution, and then my elimination is going to be the same. Here, if I compare my relative rates, my major product is actually now going to be my SN2 because I have conditions that favor it in both my stronger nucleophile, weaker base, and aprotic. And that pushes this to about 75% product formed, versus my other one being minor at only 25%. So here's where you're going to be looking at a variety of conditions and trying to kind of differentiate between those. The one other kind of key condition that we can do a lot of changing, you'll see often, I've kind of already mentioned this in some of the elimination videos, is the use of heat. As you add temperature, you're going to strongly favor elimination. So here we're going to have a reaction. We're going to do, we have a structure, secondary, which can kind of go in between, and we're going to use sodium hydroxide with a protic solvent mixture. These can go, again, both SN2 and E2. If I show my SN2, I would substitute that bromine for my alcohol. If I do my E2, I would make my double bond. When I run this at 40 degrees C, you actually get a pretty even mixture. You get about 50-50 for the two different products. If you increase that up to 100 degrees, you're going to favor your E2 significantly more, and that makes that down to about 29 to 71%. So you can see as you increase your temperature, you're favoring your eliminations. Most of the time, what you'll see is rather than me actually listing a condition, you will actually see a delta or a triangle. If you see that delta, that is going to give you a big hint that we want to do elimination. So let's kind of do a kind of summary or conclusion of some preferences for your SN2 versus your E2. For your SN2, you're going to favor a weak base / strong nucleophile, where E2 is going to favor your strong base. If you are thinking about solvent, your SN2 is going to favor your aprotic solvent, where your protic solvent is going to prefer your E2, and both of these are polar. So polar aprotic and polar protic. And protic means ability to hydrogen bond. Low temperature will favor SN2, where high temperature will favor your E2. You'll often see that as a delta. If I was going to do low temperature, I might say like 0 degrees C or an ice bath. In terms of your substrate, you're going to favor little amount of sterics. So that's going to be things like a methyl or a primary, where your E2 is going to favor maximum amount of your sterics. So especially tertiary are really going to favor your E2. We're going to build all of these up into a big table in our next video to talk about. Now, in terms of your SN1 and your E1, their rate determining step is the formation of a carbocation. So those are going to have a lot of ties. Those are going to favor heavily substituted substrates, so your secondary and your tertiary, especially in your polar protic solvents. Because of the fact that you don't want E2 to happen, E2 happens in a base, basic conditions. Most of the time, if you're trying to do SN1 or E1, you're going to favor neutral or acidic conditions. You're normally going to have both a mixture of SN1 and E1. So typically, I would maybe use temperature or something to kind of like help you force one or the other. You might also have one where you actually have no protons to actually abstract, so it has to do SN1. A lot of times, if you draw both the SN1 and the E1, that's more likely. So that's kind of like a quick snapshot. What we're going to do in our next video is we're actually going to work through a giant table where we're going to compare all the conditions for SN1, SN2, E1, and E2 in terms of kinetics and substrates and things, and then kind of build up kind of a matrix for how we decide what reaction is going to progress in some given conditions. And then in class, we're going to do a bunch of practice of, here's a reaction written out. What are the telltale signs to think about? Is this going to go SN1, SN2, E1, or E2? But I think that's good to stop this video.